All right, so last time we were looking at the buffer region. The buffer region's this region in between the initial acid and the equivalence point here. And so this is the buffer region. What were the types of calculations that we did for the buffer region? And so when we're in the buffer region, we had different calculations. For example, we had calculations where we took the milliliters of sodium hydroxide and then determined what is the pH going to be in there. And so there are different ways we can handle that. You know, to get to the equivalence point, we need a certain volume, which we'll call the volume required to reach the equivalence point, the equivalent volume. And so in order to calculate the pH, we know we're in the buffer region, so the pH is going to be dictated by the Henderson-Hasselbalch equation, which is pH is equal to pKa plus the log of the base to acid ratio. Now, if we know how many milliliters we've used, that's going to be, you know, some fraction of the volume, or it could be the actual total volume. But if it were the actual total volume, then we wouldn't be buffer. The buffer region is between the two points. And so the volume here, we'll just say X milliliters of sodium hydroxide. Then that's going to be this X over V equivalence point. This is going to be the fraction of acid that has been neutralized. And so let's say this were 25 milliliters, like in our example, and we did 12.5 milliliters. Then X would be 12.5 milliliters. Volume to reach the equivalence point would be 25. So 12.5 over 25 would be 1/2. We're at the 1/2 equivalence point. And so this fraction we call the equivalence point. You know, the, excuse me, the Z, whatever, the blank equivalence point. All right, that's the fraction of base that we're going to have. The fraction of acid that we're going to have is what's remaining. And so what would be remaining here? What would be remaining would be 1 minus X over V. And so if we neutralize half the acid, then 1 minus a half would mean that half the acid remains unreacted. If we neutralize 1/4 of the acid, that is, let's say we went to 7 or 6.25 milliliters. 6.25 over 25 would be 1/4, and 1 minus 1/4 would be 3/4. So this is the remaining acid, unreacted. So we'll just call it the remaining acid here. And so this is typically how we'd set it up. We're given X milliliters. The other type of calculation is where we're given the equivalence point. And so if we start off from blank equivalence point, let's say that 1/2 equivalence point, and then we want to figure out what the pH is. And then again, we're in the buffer region, so the pH is equal to pKa plus the log of the equivalence point. Now, the equivalence point would be some fractional equivalence point, and so we just have the equivalence point here. This would be the 1/2 equivalence point, the 3/4 equivalence point, the 1/10, whatever we want. And then we would just have 1 minus the equivalence point, where we're going to have the fractional equivalence point here. And so if we were at the 1/4 equivalence point, then we put 1/4 at the top here, and then 1 minus 1/4 would be 3/4. And so this is the amount that's reacted. This is the amount that's left unreacted. The amount that's reacted is going to produce the conjugate base. So that's why this is in the base. This unreacted is the acid here. And so this would be a calculation type B. The calculation type C is where we start off with pH and then determine how many milliliters that required. to do that, again, we start off with the Henderson-Hasselbalch because we're in the buffer region. pH is equal to pKa plus the log of the base to acid ratio. These are going to be conjugates. And so we solve for the base to acid ratio. And let's say the base to acid ratio is something called X here. Then, well, it's just going to be some number. We convert it into fraction, X over 1. Here. X over 1, this is the ratio base to acid, but this is not the equivalence point. We want to determine the equivalence point. The equivalence point, we have to do a little bit of extra. You know, X parts of the total were converted into base. One part of the total was left unreacted as acid. And so how many total parts do we have? Well, we have X over X plus 1 total parts. And so this is the fraction of the total that was reacted. This is what we call the equivalence point, the blank equivalence point. So it could be, you know, the half equivalence point or whatever. Blank. Divided by the fraction that's left unreacted. The fraction that's left unreacted is going to be 1 over the total, X plus 1. This is the fraction that remains. Fraction of acid unreacted. Okay, once we figure out what the fraction is, that is, this is going to be the fractional equivalence point, or the blank fractional equivalence point. Then we have to figure out how many milliliters. And so if we know the total volume, like the 100% is 25 milliliters, but the total volume to reach the equivalence point varies, so depending on what you start off with. So we take this fractional equivalence point like this and multiply it by the total volume to reach the equivalence point. And so if we're at the 1/2 equivalence point, then that's going to require half the volume, so 12.5 milliliters if it's 25. If we're at the 1/4, then it would be 6.25 milliliters, 1/4 of 25 milliliters, etc. And so this will give us the milliliters of sodium hydroxide required to reach that. And so these are the kind of the basic calculations that you do in the buffer section. Okay, we're going to do a few more calculations. The next calculation is we're going outside the buffer region now, and we're going to go to the first equivalence point, or just the equivalence point in this case. And so the next example of calculation is to get to the equivalence point, we have to add 25.0 milliliters of sodium hydroxide. And so we started off with 25 milliliters of acetic acid, 0.100 molar. We're going to add 25 milliliters of 0.100 molar sodium hydroxide. And so we call that an equivalent, you know, equal amounts, it should neutralize. And this is not in the buffer region. If we're not in the buffer region, we must do a solution-dilution calculation, unless you use millimoles like the book, but eventually you're going to have to convert those into concentrations or molarities. So if we did plus 25 milliliters, the first step is to do step I. With step I, the total volume here is going to be 50.0 milliliters. We're going to figure out the new acetic acid concentration. The acetic acid concentration is going to be a 25 to 50 dilution of 0.100 molar. Well, that's something we can calculate pretty easily. 0.0500 would be half. And then we need the diluted concentration of sodium hydroxide. Again, this is going to be a 25 to 50 dilution of 0.100 molar, so it's the same, 0.0500 molar. After step I, then we go to step 1. So we don't allow anything to react. We pick the strongest acid present. Strongest acid present will be acetic. Strongest base present will be sodium hydroxide. So we'll have acetic acid and sodium hydroxide. This is going to be 0.0500 molar. This is 0.0500 molar. Okay, this is going to form sodium acetate and water. K for this reaction is going to be what? Very large, very, very large, or very, very, very large? Very, very large. Since it's large, it's going to react to completion. This is stoichiometric, so this is going to go 0, 0, 0.0500. And so we're not left with a buffer in this case. What are we left with? We're left with sodium acetate solution. And sodium acetate solution is what we call a base solution, a weak base. Well, if it's a weak base, then it's Kb, but basically we follow the same procedure. We take the strongest acid present and the strongest base. What's the strongest acid present? Well, there's no more acetic acid. The strongest acid present must be water. The strongest base present would be acetate. And so it's going to be acetate plus water. The acetic acid plus hydroxide. This is Kb. Kb for this is Kw over Ka for acetic acid, which is going to give us 5.5 sub 5 times 10 to the minus 10. And so the next step here is we'll drop down the acetate concentration. This is 0.0500 molar. Water is nothing. This is 0. This is 0. Change at equilibrium. We're going to have 0.0500 minus x, and this will be x and x. And so we'll just plug that into our Kb here. This is going to be x squared over 0.0500 minus x. And then we'll just try the simplifying assumption. This is going to go to x squared over 0.0500, which gives us an x equal to, so 0.05 times 5.55 times 10 to the negative 10 square root. Yeah. 5.26 times 10 to the negative 6. Is that what you guys get? 5.26 times 10 to the negative 6. Is the simplifying assumption valid? Yeah, it's valid. The change is 10 to the minus 6. The initial is 10 to the minus 2. So we get 10 to the minus 6 over 10 to the minus 2 is 10 to the minus 4 times 10 squared gives us a percent change of 10 to the minus 2. 10 to the minus 2% change is small. And so no problem. The simplifying assumption worked well. And let's double check these. This is going to be 5.26 times 10 to the minus 6. This is the same. This is going to be about 0.05. And so let's double check K to make sure it works out. So I'm going to square this in my calculator and then divide it by 0.05. And it comes out to 5.55 times 10 to the minus 10. And so K checks out. We're good. But should we worry? We're going to generate some. This is a base solution. In base solutions, we look for hydroxide producers. So we have acetate, Kb. Should we worry about Kw, water? Yes or no? What's the most hydronium water will donate to this? What's the most hydronium water is going to donate? Yeah, 10 to the negative 7 molar. So if I have 10 to the negative 7, if I start off with 10 to the minus 6 and I add 10 to the minus 7, that is significant, right? That's a significant addition. But, you know, the only way I'm going to get 10 to the minus 7 is if there's no common ion. You know, I start off with 0 and 0. But if I have common ion there, then the actual amount of hydroxide I'm going to get from Kw is going to be much less than 10 to the minus 7. How much less? And so should I worry about Kw? I mean, this is a very tiny concentration of hydroxide. Should I worry about KW? Maybe, maybe not. What do you think? Well, if you're uncertain, the best thing to do is just try it and see if KW contributes much additional hydroxide. And so can you go ahead and calculate how much additional hydroxide we're going to get from KW in this particular problem? Should we skip it or should we not? Well, we don't have that much hydroxide in this solution, so maybe we shouldn't. So did you get it set up like this?
Yep.
Did you try the simplifying assumption or did you skip it? You tried it? Might as well try it. What did you get as your x value?
1.90 times 10 to the 9.
Does the simplifying assumption work? Is it justified? Yeah. I mean, this is 10 to the minus 9 divided by 10 to the minus 6. Give us 10 to the negative 3 times 10 squared gives me 10 to the minus 1%, less than 5%. And so the SA is okay. The percent change is way less than 5%, and so it worked. But take a look. How much hydroxide did we actually get from water? 10 to the minus 9. Why didn't we get anything close to 10 to the minus 7? The reason is because we have a lot of common ion there. The concentration of hydroxide can't grow too big because for every hydroxide produced, a hydronium is produced. A hydronium is going to be attacked by this. And so this is kind of the predator. Even though it's a very small amount, it's plenty to keep the population down of hydronium and hydroxide from water. And so was it really necessary to do this? No. A KW wasn't necessary. And so when I said the most you're going to get from 10 to the minus 7, the most you're going to get is 10 to the minus 7. It's nowhere near. It's actually a lot less than 10 to the minus 7. more like 10 to the minus 8, 10 to the minus 9, something like that. Now, we would worry about it if this were smaller. If the amount of hydroxide that we got from step 2 here was like 10 to the minus 8, 10 to the minus 9, then I'd start worrying that Kw is probably going to be a significant contributor. We saw that in an earlier calculation when we had 10 to the minus 8 molar HCl, and Kw contributed 90% of the hydronium. But anyway, we can calculate the pH based on this. Since we did this third step, when we add this to this, it's not really going to change the pH at all. What does the pH come out to? Well, first we got to calculate the pOH. And so we could have stopped here at step 2, calculated the pOH. .279, which gives us a pH of 8.720. Is that what you guys got? Okay. All right. So we have another point on the titration curve. And this point on the titration curve takes us all the way to the equivalence point. And so we started off with just the acid, and then we went through this buffer region, and now we're here at the equivalence point. Equivalence point is when we've essentially neutralized our acid. But when we neutralize a weak acid, we don't form a neutral solution, that is pH 7 solution. You know, we form something that's less acidic, that's for sure. But it's going to be pH 8.72. That's the pH at the equivalence point here. With the equivalence point of a pH close to 9, phenolphthalein would be an excellent indicator for this. Because where does phenolphthalein start to turn pink? At about a pH of 9. And so the endpoint and the equivalence point are very, very close to each other in this particular titration. And so it'd be minimal error. It still normally is minimal error, but this would be even less error. In Chem 1A, in Chem 4, we stop here. In Chem 1B, we continue on, because what's going to happen is the pH is going to skyrocket up and then flatten out. This rapid rise in pH occurs over 1 or 2 drops, maybe 3 drops, and it's done. And so it's very easy to miss this rapid rise in pH because it's so steep. It happens in just a drop or 2. And this takes us to 25 milliliters here, right? The 25 milliliters is at the equivalence point, which we determined earlier. So what we're going to do is we're going to go 1 drop past the equivalence point and figure out what the pH is. What is 1 drop past the equivalence point? Well, the volume of 1 drop is roughly how much? It's roughly 0.05 milliliters. There's kind of a number people memorize, and that's 20 drops to a milliliter. But that number isn't very accurate, and that number changes depending on the surface tension of the liquid. You know, you can grow bigger drops with higher surface tension, but small drops with lower surface tension. And so it's just a rough guide. The problem is that some people take it too literally. They think it's a very accurate number. And so when they're doing the titration that we're doing on Thursday, they just count the drops. They don't bother reading the burette because they think that each drop is exactly 0.05 milliliters. It isn't. And so when they come to calculate the molar mass of their unknown, they're way off of everything. And so you're still going to have to read the burette. We're just taking it as roughly 0.05. It's less than 0.05, actually. But we'll just say we're going to go with 25.05 milliliters of sodium hydroxide now. We start the problem over. Each time we do a calculation, we start over and say to the acid, we had 25 milliliters of 0.100 molar acetic acid. We're going to add 25.05 milliliters of 0.100 molar sodium hydroxide. And so that the total volume now is going to be 50.05 milliliters of total solution. We'll try to keep this to 3 sig figs. And so the acetic acid, we have to calculate the new concentration. We started off with 25.0, we go to 25.05. Oh no, not 25, 50.05 times 0.100 molar. So let's see what that is here. 25 times 0.1 divided by 50.05. So it's close to 1/2 dilution. It's slightly more, 0.04995. And then let's calculate the sodium hydroxide. The sodium hydroxide, we're adding 2505, and we're diluting to a total volume of 5005. And the original concentration was 0.100. So this is close to 1 to 2 dilution as well. And so it's going to be 25.05 times 0.1 divided by 50.05. 0.05004 molar. And so what we did was we just added a slight excess of sodium hydroxide, kind of 1 drop excess of sodium hydroxide. Not much. Okay, this is what called the initial, or the step I. Initial step. Okay, then we go to step 1, which is the strongest acid, acetic acid plus sodium hydroxide. This method you could use to calculate any pH on the titration curve, whether it's in the buffer region or not. There are just some shortcuts. Like in the buffer region, we have the shortcut with the Henderson-Hasselbalch. But it's not necessary to use that as long as you know how to deal with the ice tables. So let's plug in the numbers 0.04995, 0.05004, and 0. Limiting reagent would be acetic acid, so we're going to lose all of that. It's going to go to 0. This is going to be 0.04995. This is 0.00009 molar. And 0.04995 molar. Okay, so now I'm done with step 1. Where do I go next? Well, it's the same thing. For step 2, we take the strongest acid and react it with the strongest base. So what's the strongest acid present? Water. The strongest base? The strongest base would actually be hydroxide. But you know, water and hydroxide makes hydroxide and water. Does that get us anywhere? This doesn't get us anywhere, so let's pick the next strongest base. And that would be acetate. And so let's take our acetate and water, hydrolyze those. We're going to form acetic acid and hydroxide. This is Kb. We calculate Kb for acetate in the last problem. It was 5.55 times 10 to the minus 10. The amount of acetate here is 0.04995. Water is blank. Acetic acid 0. Hydroxide we have a little bit to begin with. 0.409 molar hydroxide. So this is the common ion effect. You know, this is going to inhibit hydrolysis here. And so at equilibrium, we're going to expect 0.04995 minus x, and 0.00009 plus x. So Kb is going to equal x times 0.409 plus x divided by 0.04995 minus x. But we're going to use the simplifying assumption here. Simplifying assumption means this is going to go to x point quadruple 09 divided by 0.04995, which means that x is equal to, let's see, I get an x of 3.08 times 10 to the minus 7. Is that what you guys get? All right, let's see, is the simplifying assumption justified? So let's check the percent change. The percent change here, we have two that we can calculate. We should calculate the numerator because the numerator is going to be a bigger percent change than the denominator. And so this is going to be x over point quadruple 09 times 100%. Gives a 0.0034%, 342. This is no problem. The simplifying assumption worked very well. Did we really add much to this? And so this is going to equal point quadruple 09 plus, I need 6 zeros, 1, 2, 3, 4, 5, 6, and the 308. So we're going to get point 00009 sub 0, 3, 0, 8. Now, what do you say? Did we add much hydroxide to this? Not really. Not really. We didn't add much. Which is kind of interesting because the acetate really doesn't change the pH much. The POH, if we say the hydroxide is going to generate the POH, and then we see, does that change much by the hydrolysis of water by acetate to form hydroxide? And so we barely formed any. So if we take the POH here, what is the POH here? The POH is the negative log of this. So let's see what that comes out to. Quadruple 09 log of that, 4.045. So the POH here is 4.045. What is the POH here? By adding this little bit of extra hydroxide. And so this quadruple 090308 log. 4.044. But when we round this to the correct number of sig figs, then was there any difference? No. And so this is the common ion effect in action. Here, if you look, your book calls this a strong base, weak base mixture. In a strong base, weak base mixture, your book says the pH is going to be dictated by the strong base. The weak base, because of the common ion effect, is insignificant, is negligible. And so this is very interesting because, take a look, the weak base is much more concentrated than the strong base. many orders of magnitude more concentrated. This is 10 to the minus 2. This is 10 to the minus 5. 3 orders of magnitude, roughly, more concentrated. The weak base is. So the weak base is 3 orders of magnitude more concentrated, but did the weak base contribute much hydroxide to this? No. And so all the hydroxide came from the strong base. Therefore, your book says, when you have a weak base, strong base mixture, you ignore the weak base and you calculate the pH based on the strong base. But do you want to use that as a general rule? You can, but you have to remember there are exceptions to the rule. Right? What would the exceptions be? When would the weak base be a significant contributor? It depends on the concentration, right? Here, even though this is 10 to the minus 5, still okay. But what if we had something like this? Actually, maybe I should finish this problem. Let me finish this problem first, and then we'll talk about it. All right, so we got a POH. Hey, what about KW? Should I do KW? Nah, I'm not going to do KW. KW is going to give us what? 10 to the minus 8, 10 to the minus 9. Is that going to impact this? No. We'll skip KW. And so the POH is 4.044. I think that was it, right? And that means the pH is equal to 9.056. And so what we have here is this. Within 1 drop, the pH jumped up about 1 unit. 1 drop. And so we're here. You pick smaller volumes, you see more of an impact. So that's calculating pH. We call this region, after the equivalence point, what do we call this region here? We call this the excess base region. And actually there are 2 bases in the excess base region. There's hydroxide and acetate. The acetate's always going to be there because that's the salt we form, and then as we just add more hydroxide. But what dictates the pH in the excess base region? The hydroxide. The hydroxide dictates the pH, so we can ignore the acetate. That's from 1 drop here. And so this is the least. 1 drop after the equivalence point, we already see that the hydroxide dominates, even though it's just 1 drop of extra hydroxide. And we've got a lot of acetate in there to begin with. The only time you'd have to worry about the acetate contributing is if we added like 1/1000th of a drop, 1/1000th of a drop. Because if we did something like that, then we get something like this. Rather than having a hydroxide, let's say we had a hydroxide like this. We had a hydroxide of 1 times 10 to the minus 8 molar hydroxide. And so if you follow the rule that's given in your book, the rule, it's not a law. Laws don't have as many exceptions as rules. Rules have a lot of exceptions. If you follow the rule given in your book, then you say strong base, weak base mixture. The pH is dictated by the strong base. So I'll ignore the weak base. So I ignore the weak base and I look at the strong base. This is going to give me a POH of 8, which means the pH is 6. So I got a strong base, weak base mixture, and the pH comes out to 6. Is there something wrong with that? Yeah, there's something seriously wrong with this. What is it?
pH 6 is acidic. Do strong bases make acidic solutions? So something's very wrong here. What is very wrong? What's very wrong in this case is that the strong base isn't going to be the main producer of hydroxide in this solution. The acetate will be. And so in this case, you know, we have so little hydroxide from sodium hydroxide, it's practically just pure water. And then we have the acetate. And so this is more like an acetate solution than a hydroxide solution, sodium hydroxide solution. Does that make sense? And so this is wrong. So we look at it, you know, case by case like this, but we already saw, you know, in a practical tritation, you know, how hard is it to get such a fraction of a drop? It'd be very difficult to get that kind of fraction of a drop over, you know. If we go one drop over, already the strong base is dominating. So basically that rule holds for this region here for practical purposes. It's just when we have these unusual concentrations like this, things get screwed up. So let's go much more than one drop. So we went one drop over. Let's go a bunch of. So let's go out to the 3/2 equivalence point. The 3/2 equivalence point, or the 1 1/2 equivalence point, would be at 37.5 milliliters of sodium. So we're going to have lots of excess base now. And so the next example calculation is plus 37.5 milliliters of sodium hydroxide. We start the problem over again so that we're going to have a total volume now. We started off with 25. Now we got to 37.5. So we're going to have a total volume of 62.5 milliliters. Right? So let's figure out the new acetic acid concentration. It's going to be a 25 to 62.5 dilution of 0.100 molar. And that gives me 0.0400 molar. Then I'll look at the sodium hydroxide. The sodium hydroxide is going to be a 37.5 over 62.5 dilution of 0.100 molar. .0600. Okay, now we want to figure out what the pH is going to be here, so we'll just follow the same steps. Here, strongest acid, acetic, strongest base, sodium hydroxide. We're going to form sodium acetate plus H2O. Acetic is 0.0400. Sodium hydroxide is 0.0600. Sodium acetate is 0. These are all molar. Here. Change is going to be complete. Limiting reagent here is acetic acid. That's going to go to 0. This is going to go to 0.200, 0.0200, and this will go to 0.0400. All right, what kind of solution are we left with? We're left with a strong base, weak base solution. In a strong base, weak base solution, the general rule is that the strong base dictates what the pH is. We can ignore the weak base. Is that okay here? You think? Can we ignore the weak base in this particular problem? Well, maybe not, because we have twice as much weak base as strong base, right? If we got twice as much weak base, then shouldn't the weak base be more significant in terms of hydroxide contribution? It turns out no, it isn't. Take a look at the last example we did. In the last example we had, what was it, 30 times more, 300 times more weak base than strong base, and still the strong base dictated it. Do we have to worry about the concentration here? No, the concentration here is fairly high. And so we could ignore Kb for acetate, and we could ignore Kw. And we just stop here. Well, if we stop here, that makes it easy because we don't have to do any more ice tables. This acetate doesn't really contribute much additional because of the common ion effect. And so the POH is just going to be based on this. And so we expect very little subsequent hydroxide addition from Kb and Kw. And so let's take the log of 0.02. 69 plus 14. We got a pH of 12.301. Is that okay? Skipping the next two steps? You feel comfortable doing that? If you ever feel uncomfortable doing it, why don't you just go ahead and do the next two steps and see how much additional hydroxide is contributed?
Can you explain why we can tell we can stop at step 1?
Can I explain why we can stop at step 1?
Yeah.
It's based on past experience. Past experience is the previous problem we just did. Based on the previous problem we just did, then this problem has no problem whatsoever skipping that. The last problem was more tricky. The last problem was a lot more tricky because the hydroxide was quadruple 9 molar. And the acetate was close to half a molar. So we had so much more acetate than hydroxide in the last problem. And still, the acetate was insignificant. Or not that significant, right? It didn't really register to the correct, to the number of sig figs were allowed. We would have gotten the same answer once we rounded it. So, in the last problem, we had a tiny amount of extra hydroxide. In this problem, we have lots of extra hydroxide. Hydroxide was dominant even when it was vastly outnumbered in terms of concentration. There's a heck of a lot more acetate. Now we have, close to double the acetate. In the previous problem, we had orders and orders of magnitude more. And so in this problem, I don't expect acetate to contribute anything. We got so much hydroxide to begin with, it will dominate the pH. These are tricky. These are really tough problems because, the book says, okay, let's make your life easier by skipping these last two steps. But actually it makes your life harder because you have to justify skipping it. If you don't have to justify it, then it's easier, but then you're ignoring it because sometimes you're going to be tricked into ignoring it when you shouldn't have ignored it.
So do we have to justify it in this example?
No. In this example, based on the previous example and based on numbers we've looked at in the past, it should be no problem. Kb is 10 to the minus 10, which is a bit bigger than Kw. Kw is 10 to the minus 14. And the most hydroxide we're going to get from Kw is 10 to the minus 7 molar, but it turns out it's much less than that. Kb for this is 10 to the minus 10, we're going to get a little bit more hydroxide, but we got a lot there to begin with, so it's not going to make any impact. And so it's based on seeing numbers. And the thing is having some kind of reference point. And so the way to gain that is by experience, by looking at different problems, because it's hard, because there are a lot of different scenarios. It's, you know, I didn't talk about this, but it's like percent ionization. You know, if we look at acetate hydrolysis, and so let's look at the percent acetate hydrolysis. It's nonlinear. It depends on the acetate concentration. So as the acetate concentration increases, the percent hydrolysis actually decreases. As the acetate concentration decreases, the percent hydrolysis actually increases. It makes things tough to come up with some simple, you know, when things behave non-linearly, it's tough to come up with some simple number cutoff. You know, it'd be great to say acetate's always 1% hydrolyzed. If acetate's always 1% hydrolyzed, then we can come up with a simple number saying above this number, do this, below this number, do that, right? But because of this non-linear effect, we can't come up with a simple number because the relationship is much more complicated. Now for strong acids, it's easy. I mean, strong acids and strong bases. So since I'm dealing with a base here, let's go with strong bases. Strong bases are 100% hydrolyzed, no matter the concentration. And so this is a simple relationship. This is a much more complicated relationship here. And so we just try to get a feel. So for example, in the morning class, if you look at the video, I did it with 10 milliliters. If we do the titration with 10 milliliters of 0.100 molar, then this picture looks more different. The acetate contribution is even smaller, way smaller, in step 2 of the previous problem than in step 2 of this problem. And all that was different was we titrated 25 milliliters instead of 10 milliliters. And so because of all these variables, it's hard to come up with a simple scenario. So what you do is you just register numbers. One of the numbers I wanted you to register in your mind was 10 to the minus 7, right? And 10 to the minus 8. That's why I use those particular numbers in class. And this is why I do it with 1 drop. 1 drop of excess base, and we already know that we can skip step 2. At 1 drop of excess base, we can skip step 2, then that means we can skip step 2 for everything after 1 drop. Everything before 1 drop, maybe we can't skip step 2. These are the numbers that you remember, or try to. Especially then we're going to have another type of calculation. Next example is we want a pH equal to 11.00. How many milliliters of sodium hydroxide do I have to add to get to that pH? If I want a pH of 11.00, the first thing I have to ask myself is, what region of the titration curve is this in? Is this in the buffer region? No. This is going to be in the excess base region. So if it's in the excess base region, then that means that this pH of 11.00 gives us a pOH of 3.00. Which means that gives us a hydroxide concentration total at equilibrium of 1.0 times 10 to the minus 3 molar. So in the excess base region, what are the steps? In the excess base region, I have step I, then I have step 1. Step 1 would be the acetic acid goes to sodium hydroxide. Then I have potential step 2. Step 2 would be Kb for acetate. And then I have step 3, which would be Kw for water. And so after step 1, I get hydroxide and acetate, strong base, weak base. And then I do step 2, Kb for acetate, and step 3, Kw. At this particular pH, I'm well into the outer reaches of the titration curve. I'm well past the equivalence point. The equivalence point is long gone. That was 8.7. We're now at pH 11, which is way out here. pH 11. Well, how far out there? How many milliliters is that? And so this is the total hydroxide from all the steps combined, right? This is the amount of hydroxide I got at the end of this. So where's the end, you know? So that's the hydroxide at the end of step 3? Yes, it is. It's supposed to be. This is going to be the amount of hydroxide at the end of step 3. But did step 3 really contribute much to that hydroxide? No, probably Kw contributes nothing, because the most Kw can contribute to this hydroxide is 10 to the minus 7, and it's probably going to be a lot less because of the common ion effect. So we're looking at 10 to the minus 8, 10 to the minus 9. Do you think step 3 really contributed much to the total hydroxide here? No, I don't think it contributed much of anything, right? Okay, then we go to step 2. Do you think Kb for acetate contributed much? No, I mean, we got tons of extra hydroxide in here from sodium hydroxide. Acetate already lost its dominance well before 1 drop of extra sodium hydroxide. And so do you think step 2 contributed much to the total? No. And so this makes the problem a heck of a lot easier, because this should be the hydroxide at the end of step 1. And so, oh, if that's the hydroxide at the end of step 1, then we only have to work backwards from 1 step rather than multiple steps. It's not to say that it's not that hard to work backwards, multiple steps, but we don't have to do that yet. We will have to do that in the next problem that we encounter, but we want to keep things simple for this problem. Keeping things simple, like simplifying this down to 1 step, isn't simple, because you have to justify eliminating these 2 steps. Do you feel comfortable justifying or arguing that we could ignore these 2 steps? Yes or no? If somebody asks you, why are you ignoring those steps? Would you feel comfortable convincing somebody that it's okay to do? Yes? No? If not, then do more calculations. Get more familiar with the numbers and see, what types of contributions things make. But anyway, I'm comfortable with it. And so I'm going to just go ahead and skip those. And so we go to step 1, HAC plus sodium hydroxide. This is going to yield sodium acetate plus water. And we already know what the equilibrium hydroxide should be. Oops. The equilibrium hydroxide should be this. I'm going to have some excess hydroxide, or excess strong base remaining, 1.0 times 10 to the minus 3 molar. That's how much I'm going to have remaining. But how much did I have there to begin with? I don't know. That we don't know. How much, what was the concentration? Wasn't the initial concentration of sodium hydroxide 0.100 molar? Can't I use 0.100 molar here? I can't, because of solution dilution. It's not 0.100. And because of solution dilution, I'm going to have some acetic acid concentration. I don't know what that is either. And then I'm going to have some acetate. The initial acetate is 0. But K for this reaction is very, very large. And so the limiting reagent, acetic acid, is going to go down to 0. So this is going to be minus HAC. This is going to be minus HAC and plus HAC. And so at equilibrium, I'm going to have this HAC, which was the initial. As a concentration. So we filled up the ice table, but we have a lot of blanks here. I just know the equilibrium hydroxide. This is strong base, weak base, and now I got plenty of strong base. So it doesn't matter what the concentration of weak base is. It's probably not going to factor in at all. So I got too many unknowns here. I have 2 unknowns. 1 equation, right? The K. I need more equations. How can I generate more equations for this? Well, this is step 1. So what was step I? So let's back up more. Let's go to step I. Step I started off with 25.0 milliliters of 0.100 molar acetic acid. And then I'm going to add some sodium hydroxide, 0.100 molar NaOH. But I don't know how much I need to add here. We don't know how much because that's what they're asking for. And so what I'm going to say is I'm going to add Z milliliters of 0.100 molar sodium hydroxide. Right? We're going to add some amount, Z, and actually Z is what I'm trying to figure out in this problem. And so what we'll do is we'll try to come up with some additional equations. And so when I add Z, I'm going to have a total volume of 25.0 plus Z milliliters. That'll be my total volume. And then I know we got to do solution dilution. So solution dilution, I need to calculate the new concentration of acetic acid. The new concentration of acetic acid is going to be a 25 to 25 plus Z dilution of 0.100 molar. This is what we call the initial acetic acid after solution dilution, but before reaction. That goes in step 1. And then I need to figure out the initial sodium hydroxide here after solution dilution. And the sodium hydroxide is going to be a Z over 25.0 plus Z dilution of 0.100 molar. And so I have a system of equations, multiple unknowns, and this system of equations is easy to solve. This one's not complicated like this simultaneous system of equations. And so it doesn't take much time to solve this, a few minutes, 5 minutes, and then you can calculate what Z is by doing some substitution, okay? And so solve for Z. And so when we have problems like this where we have to work backwards, we have to figure out where we work backwards from. You know, do we consider all steps or do we ignore some steps? If you consider all steps, you're safe, but the math is a lot harder. If you skip some steps, then it's a little dangerous because you might skip steps that you are not allowed to skip. But you'll make the math a heck of a lot easier. And so if you can come up with some arguments to skip steps, then you can solve these problems a heck of a lot faster. All right, any questions on this? So these are your typical calculations for titration. Let's talk about, you want to take a break and then talk about lab, or talk about lab? Yeah. Break? All right, let's take a break and then we'll talk about that.